Our next term here is melting point. This is the temperature in which a solid gets enough thermal energy from heat around it to increase the kinetic energy of the particles, and so the particles, rather than being locked in place, vibrating, particles now can move across each other like a fluid, like a liquid. So in melting point, they melt and can become a liquid. And evaporate means that the fluid particles there, when they get enough kinetic energy and start moving more, and finally break free, then they're a gas. And that's that. Evaporate can happen at ambient temperature, but boiling point is that temperature of that substance. Every substance has its unique boiling point, and at that boiling point, the liquid becomes a gas when it gets hot enough. Here is a picture of dry ice. Very cold. I'm not sure what the temperature of this is off the top of my head. But sublimation is a term here. Sublimation is when a solid can go straight to a gas without ever being a liquid. Sublimation. Here's the heating curve for water. So to explain this to you, is we have temperature there on the y-axis and heat added, more and more heat added on the x-axis. As we add a little bit of heat, it's a solid, up from that going up A, we're adding heat, the temperature is changing. But it's not changing to solid, it's still a solid even though it's getting warmer. But then at 0 degrees Celsius, the ice now is going to transition to a liquid, but it takes more. The temperature doesn't change the liquid, but you have to add more and more heat to it. But then as the temperature increases enough, then it becomes a liquid. As you add more heat, the liquid will become warmer and warmer and warmer and warmer. And then we get to a certain point right when it's boiling, right before boiling, to transition to a gas, it's going to have to add more and more heat to it, a lot of heat to it, to get it to rise just a few degrees to become a gas. And this is a lab we would have done if we would have been here. You could try to do this at home with the thermometer and look it up online. I could maybe share what I can find. This kind of is a mind-blowing idea that it doesn't change instantly from a solid to a liquid, from a liquid to a gas. It actually takes extra energy for that to happen. So here's the activity. You can pause this and sort of look and see how this is done. If you want to try it, it's kind of cool. This would be a fun way to spend some time. Here's a graph. I won't require this. Okay, but another state of matter is actually the most common state of matter in our universe, plasma. We often think about solids, liquids, and the gases as being the main ones, but plasma is what all the stars are, the sun is, and that is more than 99% of our universe are stars. And with that, what happens is the particles are moving so much that the atoms themselves can't stay together, and the electrons move off and move around free of the electrons, or free of the atoms and the nuclei, and makes for a very, very intense state of matter. Thermal expansion is the next term. With thermal expansion, as things increase in temperature, they also increase in size. You can see there that railroad track, as it got warmer, it got compressed on itself and buckled. Which also how, I guess this is what I was going to talk about thermometers. That's also how thermometers work. As they increase, the fluid in there expands, and it rises and expands with more thermal energy. Which is also how hot air balloons work. the hot air caused the balloon to expand and the density of the air inside them to decrease and expand out of there, and then allowing the hot air balloon, to carry people and rise. So water is an exception of thermal expansion. Now you see there, right there the gases are spread out. They are expanded. There's a lot of space between them. I guess I'll move myself there on the water. On the water, compared to the solids, the water is closer together, liquid water versus ice water. What happens is, in the ice, this deals with some chemistry that you may not ready for yet, but there's the hydrogens are charged oppositely than the oxygens. I'm pointing to here. And that charge, when they get slow enough, that charge will take over, and that charge will hold them in place and hold them to an arrangement, a more ordered arrangement that actually makes them bigger. Versus when water is liquid water, it is actually closer together because it's not being pushed apart by the bonds. Okay, sorry. Another type of solid is a amorphous solid. The amorphous solids are not, they're solids, but they're solids without shapes. And so I guess what it says here is they don't have a melting point, but because they're always somewhat melted, and the solid will then degrade and turn into a liquid faster the warmer it is, but they're not really solid, and so their shape is not set in stone. It is very changeable, even when it's a solid, amorphous. So it's a solid without a shape.